In life, we face many different problems and hopefully end up solving them. But what if the solution to one of those problems was worth $1 million? The problems we face can usually be sorted into two categories, easy or hard. Figuring out what to eat for dinner isn't too difficult, but deciding what to do for a living is. However, judging the complexity of human problems is subjective. What may be easy for you might be difficult for me or vice versa. But when dealing with a computer algorithm, there is a clear line between the two. And to explain why that is, let's head over to Wales.
See, a lot of problems we normally deal with, a computer would consider easy. Let's say you have a grocery list and you want to see if there are strawberries written down. At most, you'd have to search through the entire list. That takes n steps, where n is the number of items in the list. Therefore, the longer the list, the more steps it will take.
And that makes sense, right? These problems are considered P problems, meaning that the number of steps is bounded by a polynomial based on the input size. Putting that much more simply, if you had something that was n items long like that grocery list, a program that solves the problem in n squared n or n to the fifth steps is fairly efficient. A computer would consider that easy. But of course, there is also a class of problems that isn't so nice. This class, called NP or non-deterministic polynomial time, can be checked in polynomial time, but we don't have an algorithm to solve it nearly as quickly.
Suppose you're in charge of a college housing accommodation. There are 400 students and only 100 of them will actually get a room. So all you have to do is come up with a list of 100 students. That's easy enough. But then the dean walks in and gives you a list of pairs of students that can't live together. Now the problem is much harder. See, if you have a list of 100 students, you can quickly check to see if two incompatible students got paired together. You could just scroll through the list to check for any mistakes. However, if you were to come up with the list yourself, there would be so many ways of choosing the 100 students out of the 400 that you'd never actually get an answer. In the worst case scenario, to ensure that no two incompatible students got put together in a room, you'd have to come up with every one of the possible combinations. And even if you had a computer that could generate 100 of these combinations every second, it would still take longer than the age of the universe to get through them all.
So NP problems can be quickly checked, but not quickly solved. Or can they? One of the biggest unanswered questions in all of mathematics and computer science is whether or not P is equal to NP. And if you can provide a valid proof either way, the Clay Mathematics Institute will give you $1 million. No joke. This is an actual thing.
As of now, we know that all P problems are also NP problems. If I said that the product of 12 and 38 is 456, you can quickly check to see if I'm right. In fact, you'd probably just solve it yourself since it takes so few steps to do so. But there may be some problems that simply don't have a fast solution. Or, as some people think, maybe NP problems can be solved in polynomial time, but we just haven't figured out a clever solution yet. There's a famous problem called the travelling salesman, in which you have to travel to a large number of cities exactly one time each and end up back where you started. However, you're on a budget, so you want to see if there is any paths between the cities that you can actually afford. In other words, you want the shortest distance.
Now this particular problem is something called NP-complete. Skipping over some of the technical details, this means that if an efficient solution can be found for this problem, it can also be used to solve every other NP problem. But this only works if P is actually equal to NP. But judging by how many brilliant mathematicians and computer scientists have worked on these problems, it's fairly likely that the two aren't equal. However, if they were equal, we would have a major problem. See, internet security, which uses modern cryptography, relies on the fact that NP problems are hard to solve. If it was discovered that they're actually easy, let's just say that a new way to encrypt your data is going to be in high demand. So let me know, do you think that P is equal to NP? Tell me why or why not in the comments below. And if you like the drawing aspects of this video, make sure to go subscribe to my friend Einsteinium. We did a video over on his channel all about chaos theory, so if you've ever heard of the butterfly effect, you'll definitely want to go check that out. He's incredibly smart and makes awesome science videos, so go check out his channel and tell him that Kaylee sent you. As always, thank you so much for watching. Give this video a thumbs up, and I will see you next week.